Hello friends, we meet here today to start a series of lectures on digital electronics. During this journey into the fabulous world of digital electronics, we shall be talking about the various intricacies involved. Starting from the number system, we shall try to get deep insights into digital logic families, combination and sequential logic, A to D and D to A converters, and finally memories. The term digital is derived from the way computers perform operations, that is by counting digits. For many years, applications were confined to computer systems. Today, digital technology is applied in a wide range of areas such as television, communication systems, radar, navigation, medical instrumentation, industrial process control, and so on. You just name it and it is digital. The binary number system and digital codes are fundamental to computers and digital electronics in general. This lecture introduces you to the relationship of binary with other number systems such as decimal, hexadecimal, and octal number systems. Decimal numbers. You are familiar with the decimal number system because you use decimal numbers every day. Although decimal numbers are commonplace, their weighted structure is often not understood. In this section, the structure of decimal numbers is reviewed. This review will help you more easily understand the structure of the binary number system, which is important in computers and digital electronics. In the decimal number system, each of the 10 digits 0 through 9 represents a certain quantity. As you know, the 10 symbols or digits do not limit you to expressing only 10 different quantities, because you use the various digits in appropriate positions within a number to indicate the magnitude of the quantity. You can express quantities up through 9 before running out of digits. If you wish to express a quantity greater than 9, you use 2 or more digits, and the position of each digit within the number tells you the magnitude it represents. If, for example, you wish to express the quantity 23, you use by their respective positions in the number the digit 2 to represent the quantity 20 and the digit 3 to represent the quantity 3 as illustrated here. The position of each digit in a decimal number indicates the magnitude of the quantity represented and can be assigned a weight. The weight for whole numbers are positive powers of 10 that increases from right to left, beginning with 10 to the power 0 equal to 1 as shown here. Binary numbers. The binary number system is another way to represent quantities. It is less complicated than the decimal system because it has only 2 digits. The decimal system with its 10 digits is a base 10 system. The binary system with its 2 digit is a base 2 system. The two binary digits, also called bits, are 1 and 0. The position of a 1 or 0 in a binary number indicates its weight or value within the number, just as the position of a decimal digit determines the value of that digit. The weights in a binary number are based on powers of 2. Counting in binary. To learn to count in the binary system, First, look at how you count in the decimal system. You start at 0 and count up to 9 before you run out of digits. You then start another digit position to the left and continue counting 10 through 99. At this point, you have exhausted all 2-digit combinations, so a third digit position is needed to count from 100 through 999. A comparable situation occurs when you count in binary, except that you have only 2 digits called bits. Begin counting 0 and 1. At this point, you have used both digits. So, include another digit position and continue 1011. You have now exhausted all combinations of 2 digits. So, a third position is required. With 3-digit positions, you can continue to count 100, 101, 110 and 111. Now you need a fourth digit position to continue and so on. A binary count of 0 through 15 is shown in this table. Notice the patterns with which the ones and zeros alternate in each column. As you are seeing in this table, 4 bits are required to count from 0 to 15. In general, with n bits, you can count up to a number equal to 2 to the power n minus 1. Largest decimal number is equal to 2 to the power n minus 1. For example, with 5 bits, that is n is equal to 5, you can count from 0 to 31 as shown here. Similarly, with 6 bits, that is n equal to 6, you can count from 0 to 63. Learning to count in binary will help you to basically understand how digital circuits can be used to count events. This can be anything from counting items on an assembly line to counting operations in a computer. Let's take a simple example of counting cricket balls going into a box from a conveyor belt. Assume that 9 balls are to go into each box. The counter in figure counts the pulses from a sensor that detects the passing of a ball and produces a sequence of logic on each of its 4 parallel outputs. Each set of logic levels represent a 4-bit binary number. As the decoder receives these waveforms, it decodes each set of 4 bits and converts it to the corresponding decimal number in the 7-segment display. When the counter gets to the binary state of 1001, it has counted 9 cricket balls. The display shows decimal 9 and a new box is moved under the conveyor. Then the counter goes back to its 0 state and the process starts over. Here, the number 9 was used only in the interest of a single digit simplicity. The weighting structure of binary numbers. A binary number is a weighted number. The rightmost bit is the LSB or least significant bit in a binary whole number and has a weight of 2 to the power 0 and is equal to 1. The weights increase from right to left by a power of 2 for each bit. The leftmost bit is the MSB or the most significant bit. Its weight depends on the size of the binary number. Fractional numbers can also be represented in a binary by placing bits to the right of the binary point, just as fractional decimal digits are placed to the right of the decimal point. The leftmost bit is the MSB in a binary fractional number and has a weight of 2 to the power minus 1 and is equal to 0.5. The fractional weights decrease from the left to right by a negative power of 2 for each bit. The weight structure of a binary number is as shown here, where n is the number of bits from the binary point. Thus, all the bits to the left of the binary point have weights that are positive powers of 2 as previously discussed for whole numbers. All bits to the right of the binary point have weights that are negative powers of 2 or fractional weights. The power of 2 and their equivalent decimal weights for an 8-bit binary whole number and a 6-bit binary fractional number are shown in table. Notice that the weight doubles for each positive power of 2 and that the weight is halved for each negative power of 2. You can easily extend the table by doubling the weight of the most significant positive power of 2 and halving the weight of least significant negative power of 2. For example, 2 to the power 9 is equal to 512 and 2 to the power minus 7 is equal to 0.0078125. Binary to decimal conversion. The decimal value of any binary number can be found by adding the weights of all bits that are 1 and discarding the weights of all bits that are 0. We shall prove this by solving this example. We are to convert the binary whole number 110101 to decimal. In order to do this, we determine the weight of each bit, that is a 1, and then find the sum of the weights to get the decimal number as shown here. The weights for each one correspond to 2 to the power 6, 2 to the power 5, 2 to the power 3, 2 to the power 2 and 2 to the power 0, and the result comes out to be 109. So, the binary number 110101 corresponds to 109 in decimal. Decimal to binary conversion. In previous section, you learnt how to convert a binary number to the equivalent decimal number. Now, you learn two ways of converting from a decimal number to a binary number. First, we will learn the sum of a weight method. One way to find the binary number that is equivalent to a given decimal number is to determine the set of binary weights whose sum is equal to the decimal number. An easy way to remember binary weights is that the lowest is 1, which is 20, and that by doubling any weights you get the next higher weight. Thus, a list of 7 binary weights would be 64, 32, 16, 8, 4, 2 and 1, as you learned in the last section. The decimal number 9, for example, can be expressed as the sum of binary weights as shown here. 9 is equal to 8 plus 1, or 9 becomes equal to 2 to the power 3 plus 2 to the power 0. Placing ones in the appropriate weight positions 2 to the power 3 and 2 to the power 0 and zeros in 2 to the power 2 and 2 to the power 0 positions determines the binary number for decimal 9 as shown. Repeated division by 2 method. A systematic method of converting whole numbers from decimal to binary is the repeated division by 2 process. For example, to convert the decimal number 12 to binary, begin by dividing 12 by 2, then divide each resulting quotient by 2 until there is a 0 whole number quotient. The remainders generated by each division form the binary number. The first remainder to be produced is the LSB or least significant bit in the binary number, and the last remainder to be produced is the MSB or most significant bit. Binary arithmetic. Binary arithmetic is essential in all digital computers and in many other types of digital systems. To understand digital systems, you must know the basic of binary addition, subtraction, multiplication, and division. This section provides an introduction that will be expanded in later sections. Binary addition. The 4 basic rules for adding binary digits are as follows: sum of 0 with a carry of 0, sum of 1 with a carry of 0, sum of 1 with a carry of 0, and sum of 0 with a carry of 1. Notice that the first 3 rules result in a single bit, and in the 4th rule the addition of 2 ones yield a binary 2, that is 1 0. When binary numbers are added, the last condition creates a sum of 0 in a given column and a carry of 1 over the next column to the left, as illustrated in the following addition of 1 1 plus 1. In the extreme right column, 1 plus 1 is equal to 0 with a carry of 1 to the next column to the left. In the middle column, 1 plus 1 plus 0 is equal to 0 with a carry of 1 to the next column to the left. In the left column, 1 plus 0 plus 0 is equal to 1. When there is a carry of 1, you have a situation in which 3 bits are being added, that is, a bit in each of the 2 numbers and a carry bit. This situation is illustrated as follows: 1 plus 0 plus 0 is equal to 0 1, sum of 1 with a carry of 0. 1 plus 1 plus 0 is equal to 1 0, that is, sum of 0 with a carry of 1. 1 plus 0 plus 1 is equal to 1 0, sum of 0 with a carry of 1, and finally 1 plus 1 plus 1 is equal to 1 1, sum of 1 with a carry of 1. Binary subtraction. The 4 basic rules for subtracting bits are as follows: 0 minus 0 is equal to 0, 1 minus 1 is equal to 0, 1 minus 0 is equal to 1, 1 0 minus 1 is equal to 1. When subtracting numbers, you sometimes have to borrow from the next column to the left, as a borrow is required in binary only when you try to subtract a 1 from a 0. In this case, when a 1 is borrowed from the next column to the left, a 1 0 is created in the column being subtracted, and the last 4 basic rules just listed must be applied. So friends, here we come to the end of our discussion in this lecture. Therefore, we sum up. In this lecture, we learned that A binary number is a weighted number in which the weight of each whole number digit is a positive power of 2 and the weight of each fractional digit is a negative power of 2. The whole number weights increase from right to left, that is from least significant digit to most significant. A binary number can be converted to a decimal number by summing the decimal values of the weights of all the ones in the binary number. A decimal whole number can be converted to binary by using the sum of weights or the repeated division by 2 method. A decimal fraction can be converted to binary by using the sum of weights or the repeated multiplication by 2 method. So, that is it for today. See you in the next lecture. Thank you very much.